The universe is vast. It's filled with wonders we're only just beginning to understand. For centuries, we have looked up at the night sky. We used our eyes, and then telescopes, to see the light from distant stars and galaxies. But light is only one way the universe speaks to us. There is another language, a much older and more subtle one. It's a language not of light, but of gravity itself. Imagine dropping a stone into a still pond. You see ripples spread out across the surface of the water. Now think of the universe not as an empty space, but as a giant cosmic pond. This pond is called space-time. When something truly massive and violent happens, like two black holes colliding, it sends ripples shuddering through the very fabric of space-time. These ripples are gravitational waves. Albert Einstein himself predicted their existence over a century ago as part of his theory of general relativity. Yet even he was skeptical that we would ever build an instrument sensitive enough to actually detect them. But we live in a remarkable age of discovery. Scientists built incredible machines, giant detectors designed to listen for these faintest of whispers from the cosmos. And in 2015, they succeeded. For the very first time, we heard the sound of two black holes merging. It was a faint chirp that lasted only a fraction of a second, but it changed astronomy forever. Since that first historic detection, we have heard many more events from the universe's recent past. We've listened to the mergers of more black holes, cosmic behemoths that emit no light and were previously invisible to us. We have also detected the collision of neutron stars. This particular event was special because it wasn't just heard, it was also seen, confirming that these collisions are a source of heavy elements like gold and platinum. This new ability to listen to the cosmos is like gaining a whole new sense. Gravitational waves are the soundtrack to the universe. Looking deep into space is the same as looking back in time. This is because light, fast as it is, takes time to travel across the vast distances of the cosmos. There is a limit to how far back we can see with light. There is a wall that no telescope can ever penetrate. This wall is the cosmic microwave background, the faint glow of heat left over from the Big Bang. For the first 380,000 years of its existence, the universe was not transparent. It was a hot, dense, foggy soup of particles and radiation. Light couldn't travel freely. It was constantly scattered, trapped within the cosmic fog. To see past this wall of light, we need something else. Gravitational waves are that messenger. Because they are ripples in space-time itself, they are not stopped by matter or energy. They would have traveled unimpeded from the very first moments of the Big Bang. If we could detect these ancient gravitational waves, it would be like hearing the sound of the Big Bang itself. This is the ultimate goal, the cosmic holy grail for physicists and astronomers. The hunt for these primordial gravitational waves is one of the most exciting and challenging quests in modern science. The greatest challenge in detecting these primordial waves is their incredible faintness. Think of it like trying to listen for the sound of a butterfly flapping its wings in the middle of a roaring rock concert. The universe has been expanding for 13.8 billion years. Just as the sound of a distant shout fades with distance, the energy of these ancient gravitational waves has been stretched and diluted over cosmic time. The rock concert is all the other gravitational wave signals from more recent, louder events. Colliding black holes and neutron stars all over the universe are constantly creating their own ripples. Our current detectors, like LIGO, are incredibly sensitive, but they are tuned to listen for the high-frequency chirps of merging black holes. The primordial waves from inflation are expected to be at a much lower frequency. It's like trying to hear a whale's song using a microphone designed to pick up a bird's chirp. To hear these deep cosmic bass notes, we have to leave our noisy planet behind. This is why the future of this search lies in space. Scientists are designing a new generation of gravitational wave observatories that will orbit the sun, like the Laser Interferometer Space Antenna, or LISA. One of the most persistent challenges for ground-based detectors is the Earth itself. Our planet is a living, breathing, and constantly vibrating world. It is never perfectly still. The sources of this earthly hum are everywhere. The ground beneath our feet is constantly shaking with tiny tremors caused by ocean waves crashing against coastlines, cars, trains, and industrial activity. To combat this, The observatories are marvels of vibration isolation. The mirrors are suspended in complex, multi-stage pendulum systems that act like the world's most sophisticated shock absorbers. Beyond Earth's noise lies an even greater challenge, the astrophysical foreground. Our own Milky Way galaxy contains hundreds of millions of binary star systems, constantly churning out faint but steady gravitational waves. Most are too weak to be detected individually, but their combined effect creates a continuous, confusing hum. It's a gravitational wave fog that permeates our galaxy. Scientists must become cosmic sound engineers, trying to isolate one faint instrument from an entire orchestra playing at full volume. The most exciting plan for a space-based observatory is LISA. It will consist of 3 spacecraft flying in a perfect triangular formation, each side of this triangle an astonishing 2.5 million kilometers long. Inside each spacecraft is a small, freely floating cube made of gold-platinum alloy. These cubes are the heart of the detector, shielded from all external forces, so their motion is influenced by only one thing: gravity. This enormous scale is perfectly tuned to be sensitive to the long, slow waves produced by cosmic inflation. LISA is our best hope for directly detecting the primordial gravitational wave background. Another group of astronomers is using a brilliantly clever method. They are using the entire galaxy as a giant gravitational wave detector. This incredible project is called a pulsar timing array. It works by using pulsars, incredibly dense spinning remnants of massive stars. As they spin, they emit beams of radio waves. The best ones are nature's most precise clocks, more stable than the best atomic clocks we can build on Earth. If a very long wavelength gravitational wave rolls through our galaxy, it will subtly warp space-time between us and the pulsars, slightly altering the travel time of their radio pulses. Imagine the history of the universe as a grand and ancient book. Our telescopes have allowed us to read most of the chapters, but the story of what happened before the first page has remained unwritten. The primordial gravitational wave background is the ink that can finally write that first page. Finding this signal would give us the power to see beyond the wall of light that has blocked our view. It would be the ultimate archaeological dig, uncovering not the ruins of an ancient city, but the very foundations of space and time themselves. Why do we do it? The answer lies deep within us. It is part of what makes us human. We are a species defined by curiosity, with an innate, unquenchable desire to understand where we come from. We are tiny, fleeting beings on a small rocky planet, yet we have the audacity to try and listen to the sound of our own creation. It is a truly remarkable ambition. These grand scientific endeavors remind us of what we can achieve when we work together toward a common goal. The search for our cosmic origins is a project that belongs to all of humanity. The field of gravitational wave astronomy is still incredibly young. We are like an audience that has just walked into a grand concert hall. So far, we have only heard the first few loud notes from the orchestra. The next few decades promise to be a golden age of discovery. On the ground, upgraded detectors will map the nearby universe with breathtaking clarity. In space, missions like LISA will open a completely new window onto the low-frequency universe. And woven throughout all of this will be the ongoing, patient search for the ultimate prize, the primordial background. One day, we will finally hear it. The whisper will become clear, and the symphony of creation will be revealed. So the next time you look up at the night sky, remember that there is more than meets the eye. Beyond the silent twinkling stars, the universe is alive with sound. It is filled with the echoes of ancient cataclysms and perhaps with the faint resonant hum of its own creation. A whisper from the dawn of time is traveling across the cosmos, and we are learning how to listen. The journey continues. The cosmic mystery is waiting to be solved. And the universe, full of endless wonder, still has so many secrets to share.